In this example problem, we have two constant velocity toy cars that are on a collision course. You've got the red car starting at a position, the blue at another. They each are given with a velocity, and they're asked, where did the two cars meet? All right, so when you read this problem, hopefully you vision these two cars going towards each other and colliding at some point. And it's always helpful to draw a picture. So we have two positions. We have a negative 3.2 meters and a positive 7. Again, the signs are indicated with these values, right? And so we now have a convention that's given by the problem. So let's draw a number line. We have some number line. We've got one car. Now, a general convention, let's call this our red car. And generally, we're going to say that the positive direction is to the right, which means the red car now is at a position of negative 3.2 meters. And if positive's to the right, then that means the blue car would have to be over here if it is located at a positive position. Right? So we're going to mark where that blue car is located at positive 7.0 meters. So I've got this picture here. They're also moving. The red car is moving to the right. So I'll draw a little arrow here. And I'll label that arrow at 0.8 meters per second. And we have the blue car moving to the left. And the blue car is moving faster, 2.4 meters per second. That's 3 times faster. And this arrow I just drew, we call a vector arrow. And when we draw vectors, we draw the length to represent the magnitude or the amount. So 0.8 is the amount. Well, then 2.4 better be 3 times as long. So we'll get in the habit of drawing these arrows, and I'll label this 2.4 meters per second. I've drawn it longer than 0.8 just to represent that magnitude. All right, so we've got these two cars rolling around. If I'm drawing my number line, I'm probably going to indicate where 0 might be located. That's always helpful. There's 0 meters. With this car going a lot faster, let's make an estimated guess. And again, this we actually might be wrong, but I'm going to guess that this blue car, because it's going 3 times as fast, is going to end up covering a lot more ground than the other one. And let's pick our collision point where these things collide, right? So I'm going to put a little dotted line, where these cars have now collided. We're just taking a guess. It's always helpful. And the closer we can be to guessing correct, the more that the numbers we get at the end are going to make sense. All right, so where do we start from here? Well, as a physics student, we have to understand, well, we have cars moving at constant velocity. And anything in the universe that moves at constant velocity follows this model. Where it's located at some later point is equal to its velocity times the time that it's traveled plus where it started, its initial position. This is for anything with constant velocity. So because these cars are constant velocity cars, we know that they will fit that model. Now, they're different cars going at different speeds and starting at different locations, so their equations are different as far as what their numbers would be, but the model fits, right? It's going to fit this form. So, like everything we do here, we're going to set up our knowns and our unknowns, and because we have two objects, we're going to set up a table for each car. So I'm going to set up a table for my red car, and I'm going to set up a second table for my blue car. So you have red, you have blue, just setting it up. Now, in other problems, you might have one object moving, but it's moving at different constant velocities, right? Maybe a constant velocity for one period of time, then another velocity at another later time. Well, I would set up two tables for that situation as well. But anytime you get two objects, they have to have their own table. And what do we put in the table? Well, we have our TVX table, time, velocity, and in this case, we have two positions because the position's changing when this car is moving, and I can write those down. And the blue car is going to have time, velocity, x initial, and x final. Now, because they're different objects, you might give them a subscript. This might be the red's time, the red's velocity, the initial for the red, and the final for the red. You have the time for the blue, velocity of the blue, right? So you can do another subscript. You'll find that that can benefit you at times just to make sure we're not messing things up. And let's plug in what we know. Well, what we don't know is when they're going to collide. They didn't give us anything about a time. There's going to be some time that travels. And so I don't know. I've got time is unknown. So I don't know when the red car is going to collide. And I don't know how long it's going to take for the blue car to collide. The velocity of the red car. Well, they give you a speed of 0.8 meters per second. But remember, velocity has direction. We're calling to the right positive, and we drew the arrow to the right. So it's important that we put the positive zero point 0.8 meters per second. We will always put the sign with the velocity, just to be sure. And if you look at the blue car, it is moving left, which is why we're going to put a negative next to that velocity and put its value, 2.4 meters per second. Always include the units as well, because they need to match up. Initial position, where does the red car start? It starts at a negative position, negative 3.2 meters. Now, in the real world, we might not use negative positions. You might have them, but oftentimes, you'll start at zero and count up. But it's important to understand that you can have negative positions, and so this problem's set up that way. The blue car starts at a positive position. Right? It's to the right of the origin of or 0 meters. And where will they collide? Well, that's going to be right here at some point. Both cars are going to be at that location, but it's unknown. Right? And this is where we kind of get stumped here, right? I've got two sets of data, but I have two unknowns. And if you tie back into your algebra class, well, if I only have one equation, this equation, then I need to have everything except one variable. But I can't solve anything for the red and I can't solve anything for the blue. And so we got to start using our brain here and some physics and understand, well, look at the picture I just drew. What is true about this final position for each car? Well, if they collide, they're going to be in the same final position. So those are going to be equal. And if you put a stopwatch in each driver's hand, they would read the same time when they collide, right? And so you end up with a situation where, yeah, you've got an equation for the car. The red car is going to look like positive 0.8 meters per second times its time, the time for the red, plus the initial position for the red car, which we can plug right in as negative 3.2 meters. And you have another equation for the blue car, which says that the final position for the blue is equal to its velocity, negative 2.4 meters per second, times the blue's time plus its initial position, right? But because those variables are the same, we know that x final for the red is equal to x final for the blue. We can just call it x final. And the time for the red is equal to the time for the blue. So we'll just call that t, which means we really have two equations with the same two unknowns. And so I can write out these two equations, and we have now, instead of x final in the red, let's just call it x final. Now, if you look at the units, I have meters per second and meters. Everything's in meters and seconds, so I don't have to worry about my units at this point. I'm just going to write the magnitudes or the values, and I'm going to write out my equation for the red car to be here, and the blue car now is x final is equal to negative 2.4 t plus 7. And now we have two equations, equation 1 and equation 2, to represent each car. And your math teacher would tell you you can find the x and t. There's only one position and time that will satisfy both equations at the same time. And we are now dealing with, in math, something called a system of equations. A system of equations, if we have two equations and two unknowns, we can solve it. We have two equations and two unknowns, we're in good shape. If I had three unknowns, I would need three equations. Well, how do we solve a system? Well, we have three techniques. We have substitution. Now we just have a math problem. Substitution, you have elimination, and there's different ways to eliminate. You can multiply first, you can divide first, you can do some different things that way, and then you can solve it by graphing. Most people are comfortable with substitution. And again, both equations have one variable by itself, so substitution is a pretty easy math situation. I think I spelled substitution wrong. I can repair that. Substitution. All right, well, let's solve this really quickly. We're going to find that one time and position that are satisfied. And so I'm going to use substitution. I'm going to take equation 1, which says that x final is 0.8t minus 3.2, and I'm going to substitute this x final into that one. And it gives me one equation, negative 2.4t. I'm substituting the second equation into the first one, and I end up with 0.8t minus 3.2. And now I have one equation with just one unknown. We have time in that equation. All right, so now let's just do a little bit of math here. I'm going to, let's get t's on one side. All right, so I'm going to add 2.4t to both sides. And let's get the other ones. That's getting rid of that. And let's also add 3.2 to the other side. I'm just doing two steps at once, right? And I end up with a new equation that says 10.2 is equal to, what is that, 3.2t. And to solve for time, I would now divide both sides by 3.2. And that would give me a time for the collision. Let's pull out our trusty calculator. And we can type in 10.2 divided by 3.2. And we'd find that they're going to collide at 3.19 seconds. Does that seem reasonable? All right, let's look at our picture, right? They're traveling. Does 3 seconds seem reasonable? Sure. That seems like it's in the ballpark. Is that our answer? They want to know where they meet. Well, that's a position. All right, so we now know the time. They're going to collide at 3.19 seconds, which means I can plug in for either one, right? When we solve a system, once you know one variable, you can actually substitute into either equation to find that final position. So I'm going to substitute back into equation 1, which says that now x final, right? We'll use equation 1. X final is equal to 0.8 times t, which is 3.19 seconds, plus its initial starting position, which was negative 3.2. Sorry for my OneNote glitching out a little bit on me. Not liking what's going on. And when I plug in my calculator, I would get zero point 0.8 times. Now, rather than rounding, I'm going to reuse this number without rounding. I can hit second answer, and it's going to plug in 3.1875. And then I'm going to subtract 3.2 from that answer, so I can do it in one step in my calculator. And I'm going to get a position, a negative position, negative 0.65. What does that mean? X final is equal to negative 0.65 meters. What does that mean? Well, let's look at my picture. Hey, negative is just left of 0, right? And that's actually where we guessed, right? So our guess happened to be right. You won't always be right. If I got an answer positive, then I would know my picture is wrong and that they actually collided somewhere over here. But it turns out we're pretty good. This is 0.65 meters to the left of 0, right? And so this would be my answer of where they collided. They would collide at a position left of 0 by 0.65 meters. Right, so again, this is a pretty good example, pretty long-winded. I hopefully explained it well for you of why we take these steps. What's nice is if we know it's constant velocity, we can really quickly plug in that velocity and initial position, and we're going to see these equations, like equations 1 and 2, a lot with two objects interacting. Where we run into issues are with signs. Make sure you write the signs with your velocities and your positions. And if you do that, and you follow your math, there's just basic algebra 1, and we'll talk about different techniques, you're going to find the solution, and hopefully that solution passes the smell test. So hopefully it's a good little walkthrough to help you on some of the problems you're going to see. Good luck.